So we'll have a revision of whatever we discussed so far. All right. Yeah, beta gamma function will start from beginning. All right. So see, the beta and the gamma functions are actually application level concepts in which uh, we can solve very complicated integrations as the by using beta and gamma functions to get a solution of the integral, definite integral, whenever the normal integration techniques are not going to work. Normal integration in the sense, I know integration of sine theta is something, integration of x cos theta is something. I know something. Okay, I know I have standard rules of integration, right, which work most of the time. But there are some situations or some scenario in which I have to integrate very complicated functions. Okay, very complicated functions in the sense they are not supported by the standard integrals. They are not the standard integral. There is no fixed rule saying that okay, this is how it has to be done. Okay, whenever that is a case, have to use a special functions and those special functions which help us in doing this is right, those functions are beta and gamma functions. Okay, now how to define beta and gamma functions? They're the function, they're standard way of representation of certain functions. Okay, so for example, see, beta and gamma functions, they can be defined in two ways. What are the two ways using which we can define? Right, these are the two ways. Okay, the way representation of beta function in this is the type 1, first type. So you can see that the first type is nothing but I am writing a definite integral 0 to 1. The variable of integration is x. Okay, x to the power m minus 1, 1 minus x to the power n minus 1 dx. If you see this kind of function anyway, then we are going to call that as, sorry about that, then we are going to call that particular function as a beta function. Okay, very similar to that, we define what is called as a gamma function. So see, the gamma function is defined in terms of x. If you want to define, it is e to the minus x, x to the n minus 1 into dx. Okay, we can see that over here, right? Then other than that, I can use a sinusoidal function, sine or cos function, trigonometric function also to define. So beta function can be defined using trigonometry, using this kind of representation. Okay, so that is this. So this representation is nothing but it is the beta and gamma beta function mn defined using cos and sine. So definitions are important because everything is based on the definition itself. So when we go to the application level problems, we will come to know that if you want to solve any complicated function, you need to bring into this format first. So that's what is the application level problem. So complex problems will be given, we will bring that into the either a beta function or a gamma function. Then using the standard definition of beta gamma, we'll solve it. That's our approach. Okay. Now that's the definition of beta function. Similarly, you see the gamma function is defined like this. Okay, it's 2 times 0 to infinity e to the exponential. We are going to use a exponential in case of a gamma of n using this definition. So e to the minus t square, t to the power 2n minus 1 into dt. If we see that, then this will be called as a gamma function. So remember we need these 4 definitions in hands. Anytime we can use it. Okay, that's the first thing. Next, we have the properties coming up. So there are several properties that satisfies these beta and gamma functions will satisfy those conditions, those properties. We will be using the properties to solve the complicated integrals at a different stage. So we need to know what properties are there. So when we say that there is a property, we need to prove it. Okay, so we try to prove many of the properties which we see here. Okay, all right. So the property number one is nothing but m and n are the variables of the beta function. So if you swap their positions, m and n, if you interchange, the value of your integral will not change. That's what is indicated by the first property, says beta of m comma n, right, is equal to beta of n comma m. So you interchange the positions, nothing changes, it's same. We have to prove that. Okay, so we start from the left hand side, that is beta of m comma n. So this is equal to, by the standard definition, x varying from 0 to 1, x to the m minus 1, 1 minus x to the power n minus 1, right? So we use this. In this, since I want to interchange, what I do, I perform a substitution, right? Wherever I see the x, I'm going to put that as 1 minus y. Okay, which means if I take the y to other side and x to the right side, y becomes equal to 1 minus x. So in the equation where I see x, I write 1 minus y, where I see 1 minus x, I write y. So in the same equation I have a dx. Since you are changing the variable of integration, you are supposed to do a substitution for dx as well. You should remove dx and you should put dy. So how do you do that? This can be done easily. Put dx equal to minus dy, because you differentiate this function, that is y is equal to 1 minus x, y differentiation is dy, 1 differentiation is 0, minus x differentiation is minus dx. So dx can be replaced as minus dy. I also I have to find out what is the range, because x varies from 0 to 1. Whenever that happens, I'm supposed to substitute the appropriate values when I replace x with y, and we can find that when x is 0, y is 1, when x is 1, y is 0. So what I do, I make the changes in the above equation. Now the equation becomes beta of m comma n on the left side, but my variable has been changed. Variable is now y varying from 0 to 1. So because of that, now you see x is replaced by 1 minus y, and 1 minus x is replaced by y, and dx is replaced by minus dy. So whatever we found, we substituted. Sorry. Now let us substitute y is 0 to 1, the minus dy, and I'm going to make a change. If you remember, in the integration we have a property. If you have an integration from a to b, if you put a minus outside, you can make it as b to a. So 0 to 1 I can write, provided you write a minus outside. So that's why there is a minus, and we are actually performing this. Okay, exchanging the limits. Top limit becomes bottom, bottom limit becomes the top limit. Now because of this, now there is already we had a minus inside. That minus I'm cancelling. Okay, that minus I'm cancelling it out. So the first property is, if you interchange m and n, right, in the definition of a beta function, the value of the beta functions remains same. That's what is the meaning of this. So beta of m comma n equal to beta of n comma m. Okay, fine. So we prove this. So beta of m comma n, we use the first definition, x is 0 to 1, x to the m minus 1 into 1 minus x to the n minus 1 dx. Alright, in this case, since I want to interchange their positions, what I do, I use the approach of substitution. Put y equal to 1 minus x. Wherever I see a 1 minus x, I'll put y over there. That actually indicates me, if I see a x in my equation, I have to replace it by 1 minus y. Okay, and dx has to be replaced as minus dy, because if you differentiate x, it becomes dx. If you differentiate 1 minus y, it becomes minus dy. Okay, when we make a substitution, we know that in case of basic rule of integration says that you need to substitute what happens to the limits, right? So x is 0 means y is 1, x is 1 means y is equal to 0. So that's what is happening over here. Okay, so let's proceed. Let's substitute all these points in the above equation, which means Now y will vary from 1 to 0. Y is x is 1 minus y, and 1 minus x is y. There was a dx which is minus dy. So we use a property of integration now. It says that if you have a limit from, say, something like 1 to 0, I can actually exchange this if I write a minus outside. So I'll bring a minus outside and I'll write 0 to 1. Then whatever is there inside, it remains same. But I can cancel the negative sign. So there is a minus inside and there is a minus over here. Okay, so the minus minus gets cancelled and I'm left with this part. So y to the n minus 1, 1 minus y to the m minus 1 dy. So comparing it with the standard definition, if I have x to the power whatever is here, that's the first term. So I have a n here, so this is beta of n, comma, whatever comes over here, that will be the second term. So you see that it's n minus n comma m. So beta of m comma n equal to n comma m of beta function. So that's the first property. Okay, right? After this first property, we'll go to the second property now. This property is actually related to the gamma function. Okay, now gamma of n plus 1 is nothing but n into gamma of n is the basic property. Right, gamma of n plus 1, any n plus 1, it means you can write it as n into gamma of n. It's an iterative process. I can see that n plus 1 means the right hand side is 1 less than whatever is there on the left hand side. N plus 1 means it is n gamma n. Right, we need to prove that. And there is a corollary related to that. If at all the n which you are writing is an integer, positive integer, then I don't have to write n gamma n. I simply can write it as a n factorial. So this property has two parts. Okay, so to start with, let's start with the definition of gamma n. Okay, I'm using the first definition of a gamma function, 0 to infinity, e to the minus x, x to the n minus 1 into dx. Okay, now, so this means the gamma of n plus 1, if I want to replace n with n plus 1, I'm going to get this equal to integral 0 to infinity e to the minus x, x to the n minus 1 becomes n plus 1 minus 1, because every n has to be replaced as n plus 1. So I can see that here I had a n, I replace n by n plus 1. Very similarly, I can see there is a n over here, right? I can see a n here. This n needs to be replaced as n plus 1 here. So after that, I have a minus 1 by default. So, right? As a result, I'm going to get this as the answer. So e to the power minus x into x to the n into dx. So what I do for the convenience of application of integration by using integration of parts, I move their position. I swap the position. It's actually integral u into v. I swap the positions, x to the n, e to the minus x. Okay, so I bring the e to the minus x to the left, x to the n to the other side. So then I'm going to get this part. So when I have this available with me, I can actually solve this uv whenever you have a product. One of the very standard method in integration is, right, called as integration by parts. So I just mentioned that over here. We are going to use the integration by parts. Okay, so how to solve integration by parts? Let's just recall, right? Whatever is the first function, so I call the functions like this. This is a u and this is a v. V is my second function. Okay, the rule says that if you have integral uv, so you write as it is. This is u into integral of v. Whatever you have a v, its integration should be written. So I had a e to the minus x, so I am writing minus e to the minus x. Okay, this is first part of your answer of integration by parts. So since this is an answer, you can apply the limits directly. So you see, we are applying the limit 0 to infinity, which is the original limit of the problem. Once you do that, okay, after that, it's not the complete answer, so it's a part of the answer. So the second half is always, right, there is a minus. So uv, its integration uv is equal to u integration v, that's what we have done, minus integral of It's a standard definition of by parts. Integral of whatever whatever integral v you wrote, that thing should come. So minus e to the minus x into the differentiation of the first function, that is du I should write. So it is x to the n. When you differentiate, this becomes n x to the n minus 1. Okay, by using the standard definition, we are simply writing this. Okay, that's the standard definition of integration by parts. Okay, once we have this, now what we do? Now we simply substitute the limits. Right. So you see here, first I need to put the infinity. This infinity needs to be applied to this function. So when you put infinity to a e to the minus x, e to the minus x is e to the power minus infinity, which is 0. That's why the first substitution you can see here, this is 0. Okay, and now irrespective of what is there in the other side, just see 0 is substituted into x to the n. X is 0 means 0 to the power any number n is 0. So that's why the second term also becomes equal to 0. Okay, when you put infinity, second term becomes 0. When you put infinity to the first term, first term becomes equal to 0. Okay, right. Now, in the second term, you can see that there is a n which is a constant. I'll bring the n outside. N into integral 0 to infinity e to the minus x, x to the n minus 1 dx. That's as it is, right? Now n comes outside, n is as it is. If you remove n, inside this integral whatever I have is nothing but a gamma function. Standard definition of a gamma function. So I can write gamma of n. So n gamma n. On the left hand side I have gamma of n plus 1. So we proved that integration of gamma of n plus 1 is nothing but it's n gamma n. Alright, so far we never discussed that whether this n is an integer, or in the sense we are considering this as a real number. Okay, but now what we do, we make sure that n is an integer. So when n is an integer, the following steps can be added to this discussion. That is, I have a n plus 1 inside the gamma function, which is nothing but n gamma n. Same thing can be repeated for gamma n. If you have a gamma n, I can apply the same rule. 1 less than that should come over here. Correct? See, 1 less than that in the sense that is gamma n plus 1. So gamma n plus 1 is n gamma n. So gamma n can be written as n plus n minus 1 gamma n minus 1. That's what we substitute. Call this as equation 2. Substitute 2 in 1. In the sense, wherever I see a gamma n, I replace this as n minus 1 gamma n minus 1. So when you substitute that, I get this as my answer. That is equation number 3. Alright. Now, in place of gamma n minus 1, I can further apply the same rule. Right? Gamma n minus 1 is n minus 2 gamma n minus 2. Okay, I have that. Let's call this as 4. Now substitute 4 in 3. I can see that it builds up a recursive process. N plus 1, I started with this. I have n, n minus 1, n minus 2, and so on. So the last term which we can get is this. Right? If I extend this further, right, for a long time, I will get n, n minus 1, n minus 2, n minus 3, dot, 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 up to 3 into 2 into 1 into gamma 1. I can understand that from here. If this n minus 2 is 1, this is 1 gamma 1. That will be my last term. Okay, so I have a 1 gamma 1 coming up. Let's call that as equation number 5. So if you have a n as integer, n plus 1 will be an integer. So gamma of n plus 1 is an integer, which is equal to n into n minus 1, n minus 2, dot, 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 up to 1 gamma 1. So in this equation number 5, what I don't know is only gamma of 1. I have a standard definition of gamma n. I can apply that and I will try to find out what will be the value of gamma of 1. So gamma 1 is 0 to infinity e to the minus x, x to the power 1 minus 1, that is 0 dx. So because of that, you can check this now. This integration is simple, right? Simply e to the minus x, 0 to infinity. So minus of e to the minus x, 0 to infinity is minus of 0 minus 1, which is plus 1. I understand that gamma of 1 is nothing but it is plus 1. So if you put that back over there in equation number 5, what happens? Gamma of n plus 1 is nothing but n factorial. Okay, so the second half of the second property also we proved. So this is the second property which is very important. If n is integer, this is the rule. If this n is not an integer, then we know the previous one which we had written, that is n gamma n is the answer. Okay, then we go to the third property. Property number 3 is very important and very useful, very handy in most of the cases. Right? That is, if you have a beta of m comma n, I can relate the beta to a gamma function. Right? So we said that beta and gamma functions are two completely different functions that we can use in solving the integrals. The integral problems can be solved using this, but now we understand that it's not, they're not two different entities. Actually we have a relationship between them. If you have a beta, you can convert it to gamma, gamma can be converted to beta. So that's another advantage. That's why these two are studied always together. Because of this reason, you can actually interchange. Okay, so beta of m comma n equal to gamma m into gamma n whole divided by gamma of m plus n. This is what we need to prove. Okay, all right. So to start with, let's define the beta, gamma, all the functions once. Okay, so we know that since this particular function has several times definition of the gamma, right? We cannot use the same variable. That's what is the one of the rule that is mentioned in the basics of integration. Okay, whenever I use the same function twice in the form of integration, I cannot use the same variable. Okay, so for that reason, what we do, every function we'll see to that has a different variable. For example, consider the first one. Equation number 1 here is beta of m comma n. I use theta for the definition of this integral. So 2 times 0 to pi by 2 sine theta to the power 2m minus 1 cos theta to the power 2n minus 1 d theta. You see theta I am using here. At the same time, now you see I'm writing for gamma n. When it is gamma n, I'm not going to use the theta once again. I have to use a different one. In this case, by default, I'm going to use the x because already we used x as a standard variable. So I'm writing that. So you see that this is 0 to infinity twice, definitely 2 times 0 to infinity. This is e to the minus x square, x to the 2n minus 1 into dx. Okay, let's call this as equation 2. Now I cannot use theta and x in my other definition. Okay, because it also uses an integral as its integral part. So you see that what I'm writing now is this. See, I use gamma m in terms of y. So same definition, instead of x square I'm writing y square, instead of x I'm writing y, dx is replaced by dy because it is a standard gamma function. Now gamma m plus 1 also is there. I'm going to write a different variable. You can use anything, m you can write, but m and n are already defined, so I'm going to use r here. So you can see that this is r square minus r square, r to the power 2 times m plus 1 n minus 1 dr. Okay, so this definition is very important because we manipulate these variables to get our answer. So in my in the given question or in the given property, I can see that I have gamma m into gamma n in the numerator of the second half. So we'll start from there. So we try to prove that gamma m into gamma n is equal to beta mn into gamma m plus n. We will try to bring that in place so that I can move the gamma to the other side to get the required answer. So we start with the multiplication of second equation into the third equation. Second equation has a gamma n over there. The third equation has gamma m over there. So gamma m into gamma n equals to, so 2 into 2, 4, 2 times integrals, both the equation number 2 as well as equation number 3, they have integral. So the product becomes a double integral, 0 to infinity, 0 to infinity. So second equation has e to the minus x square, third equation has e to the minus y square, right? Those two I can club and write e to the power minus of x square plus y square. That's how this term comes. Now you can see that equation 2 has x to the power something, this has y to the power something. So we'll club them and write it as x to the power 2m minus 1, y to the power 2m minus 1. So then we have dx in the second one, dy in the third equation. So simply write dx into dy. So there are two integrals in this particular step. So we have two variables of integration. One is a dx, second one is a dy. Okay, in the next step, what we are trying to do here is we try to uh, make a substitution for equation number 5. Because you see the dx dy we have e to the minus x square y square we have etc. The best solution is, and the easiest way of getting a solution is converting x and y, which are rectangular coordinates, into the polar coordinates. Polar in the sense you measure, see, x and y is something like a distance. X is a distance, y is a distance. We try to replace x and y in terms of a distance and an angle, r and theta. So standard polar coordinates are r and theta. X and y can be converted into r and theta by using the following equations. These are the relationships between x, y, r, theta. So for that reason, we are substituting x equal to r cos theta, y equal to r sin theta. Okay, if you want to convert this, right, if I write x square plus y square, then I can actually replace it with r square. Why I'm looking at that? Because see, I have x square plus y square in my equation. There is a x square plus y square, so just to overcome that, I have to do this. Okay, so I find that. Then there is also a dx dy in my equation. So every dx dy I need to replace it with r dr into d theta. Okay, now the limits will change like this. So I can see that two limits are there, both are from 0 to infinity. But because of the substitution we just discussed just now, we have to make the following changes. R will vary from 0 to infinity and theta will vary from 0 to pi by 2. Okay, when that happens, see, the left hand side is still same. We started with gamma m multiplied by gamma. That should be equal to, now there's a 4 outside because 2 into 2 is 4. See, the change is this, limits we change. One was x, second one was y. Now we have r is equal to 0 to pi by 2, and sorry, 0 to infinity, and the theta varies from 0 to pi by 2. So replace the x square plus y square by r square, right? That's a change. And x is replaced by r cos theta. See, this was x to the power 2n minus 1. Now I'm writing r cos theta to the power 2n minus 1 into, this is r sin theta to the power 2m minus 1 into dx dy can be replaced directly by r dr into d theta. Okay, right. In the next step, we try to separate the variables and we try to separate both integrals, right? Just before that, we have one step. So this is 4, 0 to infinity, 0 to pi by 2, two integrations. E to the r also will keep as it is. We don't touch this, but we separate the r terms here. Now you can see that in the previous step, I have one r over here whose power is 2n minus 1. I have another r over here whose power is 2m minus 1. And also I have one more r here. So what happens to the total power? Total power becomes 2n minus 1 plus 2m minus 1 plus 1. So the last plus 1 comes because of this one. So one of the plus 1 and one of the minus 1 will get cancelled. So what remains is there is a 2m plus 2n minus 1. So that's why the power becomes equal to this. This is the power of r. Okay, then so after r has been moved out, I am left with a cosine and a sine function. Both are raised to two different powers. One is 2n minus 1, one is 2m minus 1. So you see, I'll write them as it is. Sine to the power 2m minus 1, cos to the power 2n minus 1 into dr into d theta. So r has been already moved out, so I'm left with this. Okay, right. So let's go ahead. Now I try to separate them, right? So what I do, this 4 which is present as a constant at the outside, I'm going to split it as 2 into 2. One of the two I'm going to allocate for one integral. The second one I'm going to allocate it to the second integral. So in the first integral, I'm writing one of the two and we'll write one integral, that is 0 to infinity. So that is 0 to infinity. It is applicable for r. So r should be my variable of integration. So I write all the terms containing r now. So you see, it is e to the power r square. That's actually coming from this. Okay. Then you see, r to the power this number I have, r to the power 2m plus 2n minus 1, out of which in the power I'll take 2 outside. So when you take 2 outside, this is 2 times m plus n, and there is a minus 1 into dr. So dr was here and we are bringing that over here now. Okay, after that, so all the terms containing r have been written. So now I go to my other variable, which is the theta. Theta is varying from 0 to pi by 2. So what I do, I write that 0 to pi by 2 into 2. The second 2 which was left over, I'm writing here into. Write the terms. Since you are looking for the theta as a variable, theta is this, sine theta and a cos theta into d theta. Okay, by looking at the definitions which we have used at the beginning, the first integral is going to give you a gamma of m plus n. It's very simple, because if I have a m here, this is gamma m. If it is a n here, gamma n. If since it is m plus n, it should be gamma m plus n. Very similar to that, this is the standard definition of a beta function. So beta of m comma n. So I can see that this is a product. So if you want to keep only beta, take the gamma to the denominator of other side and you are going to get this as the answer. So gamma m into gamma n whole divided by gamma of m plus n is nothing but the beta of m comma n. So the very important property also we have proved over here. Okay, right. Then using this property, we can actually find one of the very important value of a function. I told beta and gamma are standard functions. If you know the standard values, whenever you get an integration, you can replace it by its value. Okay, so one value is gamma of half. Right, if you want to go and calculate this value by using the definition, what we can do, we can go to the gamma function's definition. Maybe you can take this and put the n value as half, because gamma of half is what I want to find. It's actually, you see that this is 2 times 0 to infinity e to the power minus x square into x to the power 2 into half minus 1 into dx. That's what I am supposed to solve, but using the property I can solve it very quickly. Okay, so we'll see that now. So you see here, this is equal to, I have now this question that it's prove that gamma half is equal to root of pi. Okay, so let's find out. So beta, we start with the one property which we just have proved. What we can do, beta of m comma n is equal to gamma m into gamma n whole divided by gamma m plus n, in which I'm going to put both m and n as half. Okay, maybe it is the reason behind that is being, I want to find n equal to half. So put both of them half, we get gamma half on the right side. So what happens to this equation now? Beta half comma half is equal to gamma half into gamma half whole divided by gamma half plus half, which is gamma 1. So I know that gamma 1 is equal to 1. Already we have proved, right, in the one of the previous properties.
So we'll directly take it from there and we'll put it over here. Gamma 1, I am going to replace it as 1. So only the numerator is left over now. I don't have a denominator. So beta half gamma half is equal to gamma half into gamma half, which is gamma half the whole square. Okay, so since I have this, now what I'm going to do, I have beta half comma half needs to be found. Beta half comma half is nothing but 2 times 0 to pi by 2. Wherever I see a m, I'm going to write a half. Wherever I have n, I'm going to write it as a half. So sine theta to the power 2m minus 1 is 2 into half minus 1. Similarly, cos to the power 2n minus 1, since n is half, that's also 2 into half minus 1. So that becomes equal to what? Both powers will be reduced to 0. So in this case, you can see sine to the power 0, cos to the power 0 into d theta. Anything power raised to 0 is 1. So this is 2 times 0 to pi by 2, simply d theta. So integration of d theta is theta with the limits 0 to pi by 2. So as you can see here, when I substitute the limits, this becomes 2 times pi by 2 minus 0. Pi by 2 minus 0 is pi by 2. So 2 times pi by 2. The 2 in the numerator as well as the denominator will get cancelled. So we are left over with only what? Pi. So that was the proof which has been asked. Right? So gamma half the whole square equal to pi, which means if you want to take gamma half, take a square root on both sides, you get this answer. Okay, this is very important. Wherever we see gamma half, we can replace it directly with what is called as root pi. Okay, then we come to another very important property that is called as the duplication property of beta and gamma functions. Right? This is also this will be used many times in the problems. Okay, so that's why I'm stressing this, saying that this is very important. So previous one is important, this also important. So the property has two different phases. Okay, the first part is relating the gamma functions, converting one gamma function into different representation in terms of a gamma function. Okay, that's one thing. And the second one is actually you are converting one type of beta function into completely different types of beta function. So you see that previously we saw in one of the property we saw that beta function can be converted into gamma function, gamma can be converted into beta function. That's what one of the property. Now you see this property says that if you have a gamma function, say gamma 2m, can be written as a gamma m into gamma m plus 1. It's like you can represent a gamma function in terms of two gamma functions, product of two gamma functions. That's why sometimes it is very useful. That's why. And similarly, the beta of m comma half, right, can be written as 2 to the 2n minus 1 beta m comma m. So one format of beta function can be converted into a different beta function. Okay, right? So that's what is the this property states. It's a statement. Okay, now we come to the proof. So for the proof, we always use uh, three terms with us. One, term number two, and term number three. Okay, so term number one and term number two is nothing but it's one of the property. Property is beta of m comma n is gamma m into gamma n whole divided by gamma m plus n. We swap the sides. Left and right sides of that particular property we swap. So whenever we swap, we get this. At the same time, when you look at the second and the third term of this looks like the definition of a beta function. That's all. Straightforward, simple definition of a beta function. All right. Okay. Now what we do? I can see in the equation in the statement there is a half coming up. N value has been replaced as half in one part of my statement. For example, you see here this is a m comma n and n is equal to half. Because of that reason only I substitute n equal to half in the equation number 1. So what happens? You can see that the whole equation 1 changes to gamma m into gamma half whole divided by gamma m plus half, that is equal to, that's my first term, So we'll write the terms in the same order. First we'll write one term, then second term, and then third term, and they all are equal. Okay, so keeping that in mind, so now the equation number one, when you put n equal to half, we get gamma m into gamma half divided by gamma m plus half. That is equal to beta of m comma half. That is also equal to 2 times 0 to pi by 2 sine theta to the power 2m minus 1. But since n is equal to half, I know that cos to the power becomes 0. So you see here, this is sine theta to the power 2m minus 1 cos theta to the power 0 into d theta. Sorry, my mistake. I have written this as a theta elaborate. So this is now, this should be a d theta. All right, that's a d theta. Now, so this means, let's update. I know that in this equation, the gamma of half, right? I can write this as what? I can write that as a root pi. So you can see that root pi I'm going to write here. I replace that as root pi in this over here. Okay, and the other two terms will still remain same. The beta function, that's also same as the previous one, and the 2 times 0 to pi by 2, this term is also same. Only thing is that the cos term has been omitted, okay, because its value is going to give as 1. So let's call that as equation number 2. All right, again we'll go back to equation number 1 itself, that is this equation, and we are going to write the value as m comma m. Every n we are going to replace it as a m. Okay, so that's why this becomes equal to, now you see, after this substitution, the left hand side is gamma m into gamma m divided by gamma 2m, that is equal to beta of m comma m. I had n, now it becomes m, that's why beta of m comma m, that is also equal to, see, n becomes m. Okay, so we have sine theta to the power 2m minus 1 cos theta to the power 2m minus 1. So cos term was n earlier, but now it becomes equal to n itself. N becomes m d theta. So we use a property, right? That is, if you have the same power, right, you can write the common terms inside the bracket. So I can see in this equation that both sine and cos theta have the same power. So the same power goes out, and inside the bracket I have sine theta into cos theta coming up. So you can see that sine theta into cos theta whole to the power 2m minus 1. Okay, now we use what is called as a trigonometric identity. The identity is given by 2 times sine theta into cos theta is nothing but sine of 2 theta. Okay, but you see, I don't have the sine theta 2 theta. That format I don't have it with me right now. I just have a sine theta into cos theta. No divide by 2. So what I do, I take the 2 to the other side. In the sense, if you have simply sine theta cos theta, I can write it as sine of 2 theta by 2. That's what I'm writing here. So sine theta cos theta is there in this part. I can replace it as sine of 2 theta by 2. But the power is still remains same. Okay, 2m minus 1 into d theta. Okay, in the next step, see, the left hand side is still maintained same. Whatever was there earlier, we are still maintaining the same thing. That's why I had not written over there. Okay, but if it becomes difficult to trace, you can still write. Every step you need to have that on the left side, because we have 3 equations equal throughout this proof. Okay, now what happens? The 2 which is present in the denominator of this equation, this has a power 2 to the power 2m minus 1. So 2 to the power 2m minus 1, I can write it for the 2. So you can see that 2 to the power 2m minus 1, and in the numerator I always have a 2 which was present earlier. That 2 is there. So 2 divided by 2 to the power 2m minus 1 into integral 0 to pi by 2. Term remaining is only sine 2 theta. So this is sine 2 theta to the power 2m minus 1 into d theta. Okay, now what happens here is that normally we don't keep the 2 theta or n theta etc. inside the trigonometric function whenever you go for integration. So before we go for integration, it is always expected that you try to simplify the 2 theta, 4 theta, n theta into a single term x. Okay, so for that reason, what we do, we make a substitution now. You can see that the substitution here is 2 theta is equal to 5. So if you differentiate 2 theta, it becomes 2 times d theta equal to d phi. So if you want to keep only d theta one side, take 2 to the other side, that becomes d phi by 2. Okay, at the same time, since your substitution is 2 times theta is 5, so every limit becomes double. So 2 into 0 is a 0. That's why my limit, lower limit is still 0. But you can see that the upper limit. Now, what is the upper limit we have in this equation? The upper limit is actually pi by 2. Now, since you have to multiply this by 2, I have 2 times pi by 2, which is pi. All right. Okay. So left hand side still same. We have two equations coming up. Gamma m into gamma m by gamma 2m is equal to beta of m comma m. So after substitution, I can see that the 2 which is present in the numerator as well as the d phi by 2, that two both 2's will get cancelled. So after this gets cancelled, I can write it in this way. So left hand sides are still same. Only this rightmost part of my equation changes. 1 divided by 2 to the power 2m minus 1 integral 0 to pi, right, sine to the power 2m minus 1 of 5 into d phi. All right. So substitute. We have one more property to substitute over here. The property is straightforward. If you have 0 to pi into sine to the power k, that is, see, 0 to pi, sine power k d theta is nothing but, I can write it as 2 times 0 to pi by 2. I can actually change the limit. Limit can be changed straightforward. 0 to 2, 0 to pi can be written as 2 times 0 to pi by 2. Only that change we are going to make. So see here in this equation, this 1 is being replaced as 2 now, and the limit is being replaced as 0 to pi by 2. Okay, so let me make a change. This is actually pi by 2. Okay, that divide by is not visible. Okay, now I correct it. 0 to pi by 2 sine to the power 2m minus 1 in times phi into d phi. Okay, right. So what I do, I multiply the denominator to the other side. In the sense, this will go here as well as this is going. This will reach the other side. So because of that, now what happens? We write it in the following fashion. So after moving the 2 to the power 2m minus 1 to the other side, we get these equations. Okay, so this equation, first equation is nothing but 2 to the power 2m minus 1 into gamma m by gamma 2. You can see that comparing with the previous one. Similarly, beta m comma m we had. Now what I'm going to do, I'm going to write it as 2 to the power 2m minus 1 beta m comma m. Okay, and in the rightmost equation, the denominator has gone. Only 2 is left over. So I can write this in the following fashion. Okay, that's equation 3. Now I have copied the equation number 2 once again so that we can compare. So whatever is marked in the red square, you can see that inside that whatever I have, they are it's actually right. It's nothing but they are same. 2 to the power 0 to pi by 2, 2 times 0 to pi by 2, sine to the power 2m minus 1 phi d phi. Same thing again. 2 times 0 to pi by 2, sine to the power 2m minus 1 theta d theta. So phi d phi, theta d theta doesn't matter. They're simply variables. Okay, because they are variables, we are writing it. We can say that yes, they are equal. So if they are equal, the first and the second terms of equation 3 and equation 2 needs to be equal. They have to be equal. Only in that case the third terms are equal, because they already are equal. Everything is equal. So compare the first terms of equation 2 and equation 3. I'm going to get this. 2 to the power 2m minus 1 gamma m by gamma 2m equal to gamma m into root pi divided by gamma of m plus 2. So one of the gamma m's on both sides will get cancelled. Shuffle the terms, right? In a sense, cross multiply, you get this equation as the answer. That is first part of our property. Converting one gamma function into a product of two gamma functions is what is this. Similarly, in the same equation, equation number 3 and equation number 2, our intention now is to equate the second terms of both equations, equation 3 and equation 2, second terms. 2 times beta of m comma m is 2 to the power 2m minus 1 into beta of m comma. See, this is the second part. Conversion of one type of a beta function into a different type of beta function. All right, so that's the property called as duplication property. You can duplicate. Gamma can be converted into another gamma. Beta can be converted into a different beta. Now, as a corollary of this particular property, we have another thing to prove, like gamma half into gamma 3 by 4. Find the value of that. Right, so I start with the definition of the gamma function and its duplication property. So root pi gamma 2m equal to 2 to the power 2m minus 1 gamma m plus half. Okay, in this you substitute m value equal to 1 by 4. Why it is 1 by 4 will come to know, because I want to find the same exact value of gamma 1 by 4 and gamma 3 by 4 for that reason. So when you substitute here, on the right side you can see that you are going to get the gamma 1 by 4 and gamma 1 by 4 plus 1 by 2, which is gamma 3 by 4. In the sense, I have to retain this, move everything to the other side. While doing so, in the middle I get a gamma half in the middle. So gamma half is what I know. It's a root pi. Okay, so root pi into root pi, that's what is here. You can see root pi into root pi, right? Divided by 2 to the minus half. So 2 to the minus half is as it is. 2 to the minus half is 1 by root 2. That root 2 will go to the top numerator. And root pi into root pi, I can write it as a pi. So pi divided by 1 by root 2 is pi root 2 is the answer. This is very important. Just remember that whenever we see gamma 1 by 4 and gamma 3 by 4 in any equation, in somewhere when we solve actual problems, okay, actual difficult problems, we need to understand that, okay, I find gamma 1 by 4, gamma 3 by 4, simply replace it as pi root 2. Okay, so that's what is the uh, is a corollary of the property which we had studied earlier. Okay.